Today, lesson 7C, day number 2 of Dilations and Similarity. Yesterday, we started the very beginning of this process. We worked along with this made-up idea of a dragon head, and we did some various things based on some animators' proposals. We just basically had different coordinate rules, and we sort of tried to figure out how that would affect the dragon head. Today, we go a little bit deeper into this idea of dilations and similarity. And before we get into the new stuff, a little background knowledge. These are the things we talked about yesterday, that basically a dilation is a transformation in which a shape is enlarged or reduced by a given factor around a given center point. We talked about the fact that dilations are not rigid motion because the size is usually changing. And what that meant is that congruence is not preserved. But what that leads us to is similarity or similar figures. And last year, you talked about similar figures in detail. Two figures are similar if one is a dilation of the other. And this sort of helped you determine some of those first problems in the homework last night. And so now we're going to add on a little bit to that. And we talked about yesterday also that when we have a dilation, corresponding angles, they're congruent, parallel lines remain parallel. Slopes of corresponding sides were the same, but corresponding side length is not preserved unless the scale factor happens to be 1. And that when we use the ratios of the corresponding sides, that leads us, if they're equivalent, to the scale factor. All right, so number 1 for today, actually it's not number 1, it's just the first problem. You have this picture in your notes, and we're going to keep coming back to this picture for every piece that we add to the notes. So we are basically taking the quadrilateral. In fact, it's a trapezoid. It's a sideways trapezoid, if you want to think of it that way. Trapezoid LMNO. It's been dilated to obtain trapezoid L prime, M prime, N prime, O prime. And you can clearly see that the image is smaller than the pre-image. Okay? So some more dilation information that we're adding on to the ideas that we talked about yesterday. Corresponding vertices. Add this to your notes, please. They lie on the same line. Corresponding vertices lie on the same line. And eventually we're going to add some stuff to that picture that you have. I'm going to talk about a few things up here, and then we're going to add some stuff to that picture. So what that means is that if you were to connect the corresponding vertices, and this should be obvious, they lie on the same line, each of them. Okay, that's what I'm talking about. Second thing, the corresponding vertices also lie on the same line as the center of dilation. And I'll show you what I mean by that in just a second, so go ahead and add that to your notes. All right, so if we extend those out, like it says, we have L prime to L, and like that, and they're all going to intersect right there. Oops, I went one too far, at -6, 3, and that happens to be the center of dilation. And we're going to utilize that idea today to help us draw other figures, extending lines through the corresponding vertices. Okay? All right, next. And I don't think I need you to write down this whole thing, but listen just carefully or read along with me. It says the distance of the image vertex from the center of dilation is equal to the scale factor multiplied by the distance of the pre-image vertex from the center of dilation. And some of you are like, what in the world does that mean? Well, it's actually very simple. Okay, so let's go back to this picture right here. We just found the center of dilation, which is right there. Now what that means is that if we knew the scale factor, that would help us determine the distances between the center of dilation and each vertices. So here's what I want all of you to do right now, or each vertex. See if you can come up with your shoulder partner what the scale factor should be. Now remember, we're starting with this shape and we're dilating it down to that shape. Quickly talk with your shoulder partner. What would the scale factor be? So you have to think back to yesterday. Okay? So scale factor is 1 to 2. The second one, the image is half as big, the side lengths are half as big as the size of the pre-image. Now, going back to what I just had shown you there, what this scale factor tells us is that whatever the distance is from here to here, it's half as big as it is from there to there. Same thing from O prime to O. The distance from the center of dilation to O prime is half the distance that it is to O. And it's the same way to every single vertex. And you're going to have to utilize that thinking when you're asked to draw an image from a pre-image if you know the center of dilation and if you know the scale factor. And there's all kinds of ways that you can kind of figure that out. One of them is just by using the idea of the Pythagorean theorem. So if I ask you to find the distance from here to here, we can use the Pythagorean theorem to find that distance. By the same token, we can also, to find the distance from here to here, use the Pythagorean theorem. And so you're going to have to think a little bit, utilizing the center of dilation and utilizing the scale factor and utilizing this idea of drawing extending lines through the corresponding vertices and the center of dilation. So we're going to have to put all of those different things together. And then the last one here is segments connecting corresponding vertices. We already kind of talked about that, but go ahead and add that to your notes. They intersect at the center of dilation. All right, so we're going to start by finding various pieces from a picture, and then we're going to extend that out and start creating dilations based upon basic pieces of information. So what this means, of course, is what we already talked about, this part right here. That's how we can find the center of dilation. All right, so let's go to number one. Number one, what you need to do is you need to find three things. You need to find the scale factor, then you need to find the center of dilation, and then you need to find a coordinate rule. Now, as far as the coordinate rule goes, we need to kind of think back to how we dealt with the dragon head yesterday. So go ahead and find all three parts. One other thing we probably should clear up here, and most of you I know have no problem seeing it, but this picture is basically, this is triangle ABC right here. That's the triangle that is the pre-image. We're dilating that to find the bigger triangle right here, triangle A prime, B prime, C prime. That's what the dilation looks like. We are dilating triangle ABC to make A prime, B prime, C prime. So we started with a small triangle and we are dilating to create a bigger triangle. That means the dilation or the scale factor has to be bigger than 1. That's the only way that you can make it bigger. Now, how do we find that? We find that by looking at the ratios of the corresponding side lengths. So if we look at, for example, A prime, B prime, which happens to be right here, that has a length of 6, and we're going to compare that to the side length for AB, which is right here, and that has a side length of 3. So if we look at the corresponding side lengths and simplify them, all of them simplify to 2. That means that each of the side lengths of the image are twice as big or 2 times as big as they are in the pre-image. That gives us a scale factor of 2. Now, one other important point here is that we sometimes use the letter R to represent the scale factor, so you might want to write that down. But from here on out, I'm going to say, instead of writing scale factor every single time, I'll also give you R. So in this case, R is equal to 2. All right, next thing we were supposed to do is to find the center of dilation. Well, connect the corresponding vertices all together and find out where they intersect. Well, there's A to A prime. There's B to B prime, which happens to be right on top of that one. And then here's C to C prime. They all intersect at the origin. Therefore, the center of dilation is at 0, 0. And then a coordinate rule. This has everything to do with that dragon head problem that we talked about yesterday. The image is 2 times as big, or as far as the side lengths, as the pre-image. The image, the side lengths are 2 times as big. So that gives us a coordinate rule of x comma y turns into 2x comma 2y. And sometimes writing down the ordered pairs will help us see that if we didn't realize that earlier. Okay? Any questions about number 1? All right, everybody do number 2, all the parts, please. The pre-image is triangle ABC. That's the bigger one. The image is A prime, B prime, C prime. That is a smaller one. Therefore, the scale factor has to be between 0 and 1. The question is, what is the scale factor? Well, if I compare the lengths of the corresponding sides, A prime, B prime over AB, and to find that, there are lots of ways we could do that, but you could create some right triangles and use the Pythagorean theorem. But we have square root of 29 over 3 times the square root of 29. Square root of 29 goes into square root of 29 once. And I know that there are other ways of finding the scale factor, but that's one way. So we can see that we're going to get, when we compare the ratios, they all simplify to 1/3. Therefore, R is equal to 1/3. Or the scale factor is 1/3, or 1:3. Second thing you were supposed to find, and I'm going to keep asking this every single time, but I'll come back to this question in another problem. We were supposed to find the center of dilation, so connect all the corresponding vertices together, and that one intersects once again at the origin, or 0, 0. And then we were supposed to find the coordinate rule. Sometimes looking at the ordered pairs will help, but it should be x comma y turns into 1/3 x comma 1/3 y. Everybody turn over to the back side and do number 3. All right, so we need to find the scale factor. Once again, to find the scale factor, there are several ways. One is by comparing the ratios of the corresponding side lengths. So we have A prime, B prime over AB, which is 8/4, which is 2, and so on. And we end up with a scale factor of R equals 2. Center of dilation, connect all the corresponding vertices together. We can see for the first time it's not at 0, 0. It is at 5, 5. All right, so let's go to number 4 now. In number 4, the first thing that we're asked to do is to create a new quadrilateral that is 2 times larger than the original one with the center of dilation at the origin, and then label it correctly. So the first place that you need to start, and this just is to give you some direction, is to draw lines through the center of dilation and all of the vertices. So what I mean is something like this. Now the reason why we do that is because all the dilations that we happen to do in that situation, the vertices, or the vertexes, however you want to say that, they all will lie on those lines. And this is kind of how we started today's lesson, by having that discussion. So let's draw all those lines. Now what we are supposed to do is we're supposed to create an image that is twice as big as that one. Or in other words, the sides are two times larger. So each side will be 2 times as long as it is here. But not only that, the distance from the vertex will also be twice as far. And so I'll help you get started here. What I mean by that is that if we look at the distance to Q right here, we have a rise of 4 and a run of 2. What that means is that to get twice as far away, we would have to rise 8 and run 4, and that would give us Q prime. That's just another way of dealing with dilation. So there's Q prime, and I'll let you kind of finish it from there. So if we just continue on and extend this idea out, I showed you this way by using slopes. This is not too much different than I showed you with rotations and how you could use the same sort of idea. But when you're finished with the one that is 2 times as long, that means that the scale factor is R equals 2. That's what it should look like. Notice that every vertex is on one of those lines. Any questions with this? Okay, so now quickly do the same sort of thinking to do part B. And part B, you're supposed to create one that is half as large. In other words, the scale factor is 1/2. So for part B, we are creating one that is half as big, and so it would look something like this. And the quickest way of getting that, in my opinion, is using the idea of slope. Rise 4, run 2 to get to Q, so Q double prime would be half of that. Rise 2, run 1, and so on. And one of the questions that I had been asking in every single problem, how do you know that they're similar? Well, you would know that they're similar by comparing the corresponding side lengths. And if all those ratios are equivalent to each other, then you know that they truly are similar. Okay? So here's what we're going to do. We have 2 problems left, number 4 and number 5, and I want you to do those together with your shoulder partner. And I'll come back to you in about 3 or 4 minutes, and we will compare what you have there. So go ahead and do number 5 and number 6. All right. So one thing you should also take into consideration is this. Look, what was the scale factor in this one? 1/2? Oh, I guess I should bring that up here. Hold on. Yes, it is 1/2. So one thing you should be looking at is this. From the center of dilation to S, it's 2. That means to S prime, it's only going to be 1. From the center of dilation to T, it's 4. That means from the center of dilation to the new shape, it's only going to be 2. And whatever the distance is from there to there, it'll be half the distance for our new shape. And so what that means is our dilation looks like that. And if you didn't get that, fix it. And you can clearly see it's only 1 from center of dilation to S prime, and it's only 2 from center of dilation to 2, and it will be half the distance to there as well. When you're dilating by a scale factor of 1/2, each of the side lengths will end up being half as long. Same thing as the distance from the center of the dilation. All right, and then here is what number 6 should look like using similar thinking. So any questions about number 5 or number 6? All right, that is it for today. I'll leave this one up here for a few seconds to let people who missed it get that copy down, and we are finished for today.